Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will graph the relation, the floor of y equals x. The floor of y, written with brackets around y, means the greatest integer less than or equal to y. Our goal is to build the graph step by step and see the general pattern. First, recall the definition. If the floor of y equals n, then y sits in the interval n to n plus 1, including n but not including n plus 1. Now, let's set up axes to draw the graph. Step 1. If the floor of y is 0, that forces x to equal 0. The interval for y is 0 to 1, including 0 but not including 1. On the graph, that is a vertical segment at x equals 0, from y equals 0 up to y equals 1, with a solid dot at the bottom and an open circle at the top. Step 2. If the floor of y is 1, then x is 1, and the y values run from 1 to 2, including 1 and excluding 2. Draw the vertical segment at x equals 1 from y equals 1 to y equals 2. Step 3. If the floor of y is 2, then x is 2, and y lives in the interval 2 to 3, including 2 and excluding 3. Add the vertical segment at x equals 2, from y equals 2 up to y equals 3. To see the full picture, this pattern also extends to negative integers. For example, if the floor of y is negative 1, then x equals negative 1. And y is between negative 1 and 0, including negative 1, excluding 0. In general, if the floor of y equals k, where k is any integer, then x must equal k, and y lies between k and k plus 1, including k and excluding k plus 1. Final answer. The solutions of the relation are all points on vertical segments at each integer x equals k, with y between k and k plus 1, including the bottom point, and excluding the top point. In this lesson, we will graph the relation bracket x times bracket y equals 3, where bracket denotes the floor of the greatest integer less than or equal to a. We'll identify all integer pairs whose product is 3, convert each pair into an x and y interval, and then shade the corresponding 1 by 1 squares on a coordinate plane with correct boundary styles. First, let's write the problem in math notation and recall the definition of the floor function. Floor of a equals n if and only if n is less than or equal to a, and a is strictly less than n plus 1. Since bracket x and bracket y are integers and their product is 3, and because 3 is prime, the only integer factor pairs are 1 with 3, 3 with 1, -1 with -3, and -3 with -1. Now we convert each integer pair into an x interval and a y interval using the floor definition. Let's draw a coordinate plane and then place each of the 4 regions as 1 by 1 squares. Remember, for the floor intervals, the left and bottom edges are included, while the right and top edges are excluded. We'll draw included edges as solid lines and excluded edges as dashed lines. Now, we will add each valid region 1 by 1. First, the case bracket x equals 1 and bracket y equals 3, which means x is between 1 and 2 and y is between 3 and 4. Next, bracket x equals 3 and bracket y equals 1, which means x is 3 to 4 and y is 1 to 2. Then the negative pair, bracket x equals -1 and bracket y equals -3. And finally, bracket x equals -3 and bracket y equals -1. Watch for the included solid edges at the left and bottom, and the excluded dashed edges at the top and right. To summarize, the relation bracket x times bracket y equals 3 is represented by 4 disjoint unit squares, one between x equals 1 to 2 and y equals 3 to 4, a second between x equals 3 to 4 and y equals 1 to 2, a third between x equals -1 to 0 and y equals -3 to -2, and a fourth between x equals -3 to -2 and y equals -1 to 0. The left and bottom edges are included, the top and right edges are excluded. That completes the graph of the bracket relation. Example, we will solve the relation floor of x squared plus floor of y squared equals 1, and then graph the solution set in the coordinate plane. First idea. Since the floor of x and the floor of y are integers, their squares are non-negative integers. The only way two non-negative integers add up to 1 is that one of them is 1 and the other is 0. So we have exactly two cases to consider. Case A, the floor of x squared is 1 and the floor of y squared is 0. And case B, the floor of x squared is 0 and the floor of y squared is 1. Let's build the coordinate plane for our graph. We'll keep the grid lines at integer spacing to align with the floor function. Case A, if the floor of y squared is 0, then the floor of y is 0, which means y is between 0 inclusive and 1 exclusive. If the floor of x squared is 1, then the floor of x is either plus 1 or minus 1. That gives x in 1 to 2 or x in negative 1 to 0. Together, this makes two unit rectangles, right of the origin and left of the origin, both in the horizontal strip, where y is between 0 and 1. Case B, if the floor of x squared is 0, then x is between 0 and 1. If the floor of y squared is 1, then y is either between 1 and 2 or between negative 1 and 0. This creates two more unit rectangles, one above the origin and one below the origin, both in the vertical strip where x is between 0 and 1. Putting it all together, the four shaded unit squares form a cross pattern around the central square. Notice, the central square where x and y are both between 0 and 1 is not included because that would make both floors equal to 0 and the sum equal to 0, not 1. To build intuition, here are some valid points inside the solution. 0.5, 1.5, 1.5, 0.5, minus 0.5, 0.5, and 0.5, minus 0.5. And here are some points that are not in the relation, like 0.5, 0.5 at the center, or 1.0, 1.0 on the corner boundaries that are excluded by the half open intervals. Final answer. The solution set is exactly the union of these four half open unit squares. Top 0 to 1 by 1 to 2, bottom 0 to 1 by negative 1 to 0, right 1 to 2 by 0 to 1, and left negative 1 to 0 by 0 to 1. Their centers are at plus or minus 1.5, 0.5, and 0.5, plus or minus 1.5. That completes the graph of the relation floor of x squared plus floor of y squared equals 1. Notice how the floor function turns the curve into four clean unit blocks on the integer grid. Example, we will solve the relation floor of 2 times absolute x plus floor of absolute y equals 4. Here, square brackets mean the floor function. We'll find all pairs of reals, x and y, that satisfy this. Since absolute values are non-negative, both floors are non-negative integers. So we list all integer pairs that add to 4. 0 plus 4, 1 plus 3, 2 plus 2, 3 plus 1, and 4 plus 0. For each pair, we convert the floor into an interval and shade the corresponding rectangles on the coordinate plane. Let us set up a coordinate plane that reaches a bit beyond x equals plus or minus 2.5 and y equals plus or minus 5. We'll keep this diagram on screen and add each case to it in color. Case 1, floor of 2 times absolute x equals 0, and floor of absolute y equals 4. 4x, that means 0 less than or equal to 2 times absolute x is less than 1, so absolute x is less than 1/2. 4y, for less than or equal to absolute, y is less than 5. We will shade all four symmetric rectangles for these intervals. Case 2, floor of 2 times absolute x equals 1, floor of absolute y equals 3. 4x, 1 less than or equal to 2 times absolute x is less than 2, so 1/2 less than or equal to absolute x is less than 1. For y, 3 less than or equal to absolute, y is less than 4. Let us add these rectangles in a new color. Case 3, floor of 2 times absolute x equals 2, and floor of absolute y equals 2. 4x, 2 less than or equal to 2 times absolute x is less than 3, so 1 less than or equal to absolute x is less than 3/2. For y, 2 less than or equal to absolute, y is less than 3. We will shade these now. Case 4, floor of 2 times absolute x equals 3, and absolute x equals 3, and floor of absolute y equals 1. 4x, 3 less than or equal to 2 times absolute x is less than 4, so 3/2 less than or equal to absolute x is less than 2. For y, 1 less than or equal to absolute, y is less than 2. Add these rectangles. Case 5, floor of 2 times absolute x equals 4, and floor of absolute y equals 0. 4x, For less than or equal to 2 times absolute x is less than 5, so 2 less than or equal to absolute x is less than 5 halves. For y, 0 less than or equal to absolute, y is less than 1. Let us add the final set of rectangles. Putting all 5 cases together, the solution set is the union of these colored rectangles. Because the absolute values make the conditions symmetric across both axes, the full picture looks like a stepwise diamond centered at the origin. Any point inside any of the shaded rectangles satisfies the original relation. This completes the solution. Pause and inspect each band to see how its floor value pair creates a horizontal strip and a vertical strip that combine into rectangles. In this lesson, we graph the relation floor of y equals floor of x. The floor function returns the greatest integer less than or equal to a number. Our goal is to visualize all points where the floor of y matches the floor of x. Key idea: for any integer k, floor of x equals k if and only if k is less than or equal to x and x is less than k plus 1. The same holds for y. So the equality floor of y equals floor of x equals k means both x and y lie in the same 1-unit interval from k up to, but not including k plus 1. Let us build the graph step by step on a coordinate plane. We will plot the unit squares for several consecutive integers k, each square covering x from k to k plus 1 and y from k to k plus 1. Notice how these squares sit along the diagonal line, y equals x like a staircase of blocks. Let us zoom into one block, the block where k equals 0. In this square, the left and bottom edges are included because x equals 0 and y equals 0 lines are part of the set. The top and right edges are excluded because at x equals 1 or y equals 1 the floor jumps to 1. The corner at 0, 0 is included while the other 3 corners are excluded. Altogether, the graph is the union over all integers k of the squares with x between k and k plus 1 and y between k and k plus 1, both including the lower bounds and excluding the upper bounds. These unit squares sit along the diagonal and only touch at the included lower left corners k, k. In this lesson, we will graph the relation brackets y equals x squared. Brackets y means the floor of y. We will build the graph step by step and see why it looks like a set of vertical needles. The floor of y is always an integer. Since x squared equals floor of y, x squared must be a non-negative integer. In other words, for each whole number n greater than or equal to 0, when y is between n and n plus 1, the floor of y equals n, and x equals plus or minus the square root of n. Let us draw axes, and then add each interval one by one. We'll highlight the strip for y from 0 to 1, then from 1 to 2, and so on, and place the vertical segments at the correct x positions. Step 1. For y between 0 and 1, the floor of y is 0. That means x squared equals 0, so x equals 0 on the graph. That is a vertical segment at x equals 0 from y equals 0, closed, up to y equals 1, open. Step 2. For y between 1 and 2, the floor of y is 1. Then x squared equals 1, so x equals plus or minus 1. We draw 2 vertical segments, one at x equals negative 1 and one at x equals positive 1. Each from y equals 1, closed, up to y equals 2, open. Step 3. For y between 2 and 3, the floor of y is 2, so x squared equals 2, which means x equals plus or minus square root of 2, about 1.41. We draw 2 vertical segments at those x values from y equals 2, closed, up to y equals 3, open. Step 4. For y between 3 and 4, the floor of y is 3. That gives x squared equals 3. So x equals plus or minus square root of 3, about 1.73. Again, we add vertical segments at those x values from y equals 3, closed, up to y equals 4, open. Notice the pattern. For each whole number n, there are vertical segments at x equals plus or minus square root of n, spanning y from n up to n plus 1, with a closed dot at the bottom and an open circle at the top. We can summarize the relation like this. Final answer. The graph consists of vertical segments at x equals plus or minus square root of n for n equals 0, 1, 2, 3, and so on, each spanning y from n inclusive to n plus 1 exclusive. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.